You'll see the calculus stuff is not, okay, you'll look on this page and you'll say, okay, yeah, the calculus stuff is easy, huh? Yeah, no, it looks terrible. It's actually not as bad as it seems. But we're looking at still a little bit more pre-calc stuff. We'll start with something completely numerical, something that you could actually type right into your calculator. I could do this right now. Sine of the arc cosine of 4/5. 0.6. You want to do math frac? Just clean it up. Sure, 3/5. Great. So you could do that, but let's come up with a more general approach, not in the classic teacher sense of we have an easy way of doing it, so let's figure out a way to make it more difficult so I can kill a class period. Not like that. More so that we could apply it in variable situations. You look at 7 and 8 immediately off the bat. It's non-numerical. All right. So this is some angle theta. Theta is equal to the arc cosine of 4/5. All right. Which, based on everything that we were talking about on the previous page, corresponds to the cosine of theta being equal to 4/5. All right. So again, algebraically, it's a slight manipulation, but it makes a big difference because we know cosine ratio. We know that that's adjacent over hypotenuse. So I could draw a triangle, a reference triangle with a reference angle theta. I can place my adjacent side, make it a 4, my hypotenuse, make it a 5. What's my missing side? 3. Nice Pythagorean triple. All right. What this represents is a visual representation of the arc cosine of 4/5. All right, this triangle is the arc cosine of 4/5. Basically telling us that if I could figure out the missing angles in this triangle, I would then know what the arc cosine of 4/5 is. The good news is I don't need the arc cosine of 4/5. I need the sine of the arc cosine of 4/5. Since the arc cosine of 4/5 has been defined as theta, I'm really just looking for the sine of theta in that triangle. The sine ratio, opposite over hypotenuse. The opposite side, 3, the hypotenuse 5, 3/5. All right. I mean, it was way quicker on the calculator, but again, it didn't have any variables in it, so the calculator doesn't have a problem with it. It would have a problem with 7 or 8. But we could use a similar strategy for number 7 to come up with a ratio that represents the sine of the arc cosine of x. All right. So, bless you. This is theta. The result of an inverse trig function is always an angle. Just repeat that to yourself like 10 times, and you should be fine. All right. The result of an inverse trig function is an angle. And then, 9 more times after that. I'm not going to do it. I already memorized it, so I'm good. All right. So I could rewrite it as the cosine of theta is equal to x. Same structure as the last problem. Right, well, the x isn't a fraction. All right. Well, now it is. It's fine. Adjacent, hypotenuse, triangle. Basically the same triangle. Adjacent side is the unknown. The hypotenuse is equal to 1. I'm going to need the sine ratio, which is the opposite over the hypotenuse. Right. So I'm going to need to do basically what I did here, which is going to require me to figure out the missing side. Not a Pythagorean triple anymore, but not impossible to figure out. square root of what?
1 squared minus x squared.
1 squared minus x squared, which I'm going to simplify to just a 1 minus x squared. Good, good. All right, and so again, since we're looking for the sine of theta, which would be the ratio of the opposite side to the hypotenuse, we pretty much have it. So I'll just write my answer above. The opposite side is the square root of 1 minus x squared. And the hypotenuse is equal to 1. I'll write it over a 1 just to have it, but you obviously, if you're simplifying, you wouldn't write that. All right. This is a very powerful relationship here. It just doesn't seem like it would be. But what it does is it allows us to take something that's trigonometric and turn it into something that's algebraic. If I ask you right now to take the derivative of the sine of the arc cosine of x, you wouldn't be able to do it. Because it would be chain rule, and that's all well and good, but the inner function is the arc cosine of x. You don't know how to take the derivative of that yet. But if I tell you that these two expressions are equivalent, then you can just take the derivative of this, and it would be the same as the derivative of that. So by knowing how to convert over to an algebraic form, half the battle's already won. And also, I mean, we don't really get to too much involving antiderivatives in this course, but that's actually the part that makes calculus hard. You know, once you've mastered everything about derivatives, you know, you take a calculus class where they turn around and have you do everything in reverse. So find the expression that has a derivative that's equal to this expression. What they're most commonly going to do, if they're going to try to stump you, is give you an expression in this form, and you have to recognize that that is equivalent to taking the sine of the arc cosine or the tangent of the arc secant, whatever, and then work off of that, right? Because generally, I mean, once I show you the rules, you know, it becomes a debate where it's like, well, finding derivatives involving trig is not that difficult. Algebraically, they can be a nightmare. So sometimes substituting out an algebraic expression for a trig one is the way to go. But that's baby steps towards that. Eventually you'll get there and you'll remember this, hopefully. But until then, we're taking a lot of things on faith, I guess. All right, so, and again, we want to streamline it a little bit. Secant of the arctangent of 3x. Again, the result of an inverse trig function is always an angle. So this whole thing here amounts to some angle theta. All right? So I could write arctangent of 3x is equal to theta, just to then take the tangent of both sides. But it's all going to amount to the idea that the tangent of theta is equal to 3x. Again, trig ratios. So I'm going to write it as 3x over 1. I have my opposite side, and I have my adjacent side. That's the TOA part of SOHCAHTOA. All right. So I'll pop in my opposite side, my adjacent side. We'll just have to figure out what the missing side is. Pythagorean theorem. Again, not as easy as 3/5, but doable. And then once we have that, we're going to find the secant of our theta, which by SOHCAHTOA is hypotenuse over the adjacent. Always a good idea to kind of have in mind what you need, because if I got to this step, let's say on the outside it was like cotangent, like the cotangent of the arctangent of 3x. The ratio for cotangent is adjacent over opposite. So when I go to look for that, I don't need the hypotenuse, so I wouldn't waste my time solving for the missing hypotenuse. Right. But what would that hypotenuse be?
Radical 1 plus minus 2.
Exactly. And again, all Pythagorean theorem. All right, so I take my hypotenuse, divide it by my adjacent, and that gives me my equivalent expression, which would be that radical over 1, but again, you don't have to write the over 1 if you don't want to, but I'll do it. All right, so another algebraic expression that's equivalent to the given trigonometric expression. When you start getting into secants and cosecants when taking the derivative, algebraic expressions, a substitution might make more sense because the derivative of secant of just x is secant x tangent x. So if I were taking the derivative of this, it would be secant of the arctangent of 3x times tangent of the arctangent of 3x, that part will actually be nice, times the derivative of the arctangent of 3x. Again, we don't know that, but it would be a disastrous mess. But once you simplify that down, you get the exact same answer that you would get if you took the derivative of this with chain rule, log differentiation, whatever method you like. Right? So the benefit, I don't know. I'll say it's obvious, but there's always some disbelievers, I guess. So let's actually learn how we can come up with some rules related to inverse trig derivatives. So again, the result of an inverse trig function is always an angle. So let's call this some angle theta. All right. So I could write, I'll actually write it out more carefully this time. I won't skip any steps. Theta equals the arc sine of u. I'm purposely leaving a little space in front of the arc sine. All right, because again, the result of an inverse trig function is always an angle. The expression that's contained within, that's always a ratio. All right, so there's a little hint as to how you could skip some steps, but I'm not going to bother with that right now. I'm going to take the sine of both sides and get, well, this side's going to become a u, so I'm going to write it as u equals the sine of theta. All right, it becomes notation intensive here because you got to sort of have an idea of what it is you're looking for in a final answer. But in order to do that, you need to know what the notation is telling you. So I'm saying again that the result of an inverse trig function is always an angle. All right, I've said that. I got to be close to 10, maybe 7 or 8 at this point. But just focusing on the idea that I can replace this with theta, it tells me that what I am ultimately looking for is d theta dx. All right, that's my goal. So I have a u and a theta. So I'm already behind the 8 ball. Right? I need to somehow introduce x's here. And also, by the way, I need to get rid of u's because this just says d theta dx. Right? So what we can do, at least as a first step, is take the derivative, just as you see it. I'm going to find du d theta. All right, so if this were 2 units ago, I would give you the problem as y equals the sine of x and say find the derivative. You would say the derivative of sine of x is cosine x. All right, here I'm just replacing the u. This isn't even implicit differentiation. I'm replacing the y with a u. I'm replacing the x with a theta. So my derivative is going to be pretty much the same, except it's going to have a theta instead of an x. All right, the rest of this process is actually just going to boil down to the idea that I need to somehow make that du d theta into a d theta dx, which is kind of a weird thing to think about, but it's actually very doable. So what I might consider doing, well, I'm looking at my expression here compared to what I want. The d theta is on the bottom. I want it on the top. All right, so I'll do that. I can't just do it to one side without doing it to the other. So I'll do that. So that's something. I need some x's, and I need to get rid of that du. All right, so, but let's focus on the trigonometric part of it here. If I can get rid of that, it's going to go a long way. All right, so let's take a look at this expression here. The u equals sine of theta.
Why would you want to get rid of that and not the d theta or the du?
Well, we're going to get rid of them both.
But you have to get rid of cosine theta?
Yeah, well, I'm going to show you how to get rid of both. I'm just starting with this. All right, so sine of theta is u. So we could write it as a sine of theta equals u over 1. I'm going to draw a triangle. All right, so the skills from the problems that are right above this, the 3 examples, are going to come back into play right here. The sine ratio is opposite over hypotenuse. All right, so opposite would be u, hypotenuse would be 1. What I need is the cosine ratio. Now, you may even look at this and say, well, 1 over cosine, I could change that into secant, but I'm not going to do that right now. What would the missing side of my triangle be? The square root of something. 1 minus u squared? Yep. All right, so 1 over cosine. I can change that now because, yeah, so 1 over, adjacent over hypotenuse for cosine, which would be the same. 1 over a over h would correspond to h over a. All right. So before, when I was saying I could take my 1 over cosine theta and make it into secant, I could do that, but it's all going to come out in the wash anyway, because the ratio h over a is the ratio for secant anyway. All right, so you can grab it either which way. So my hypotenuse, which is 1, would be over my adjacent, the root of 1 minus u squared. All right, so almost there. The grand finale coming up. We have a d theta du. I'm going to leave a little space, then an equal sign. 1 over the root of 1 minus u squared. All right, again, don't lose sight of the goal. I got rid of my cosine of theta, that's great. I have an algebraic expression to take its place, but it's in terms of u, so that's a little annoying, but I can deal with it. The big issue is I need a d theta dx instead of a d theta du. All right?
Why do you want the d theta dx?
Because that's what they're asking this for. It's d dx of this theta.
Okay.
So that denominator there is telling me what I need to have my final answer in terms of.
So, oh, okay. Yeah.
All right, so we can multiply that ratio by a new ratio that's going to keep the d theta the way it is, but get rid of the du. What would that ratio be? Du dx. Good, good. But you can't just multiply to one side without the other. All right, so that's a little chain rule aspect to it, because any time we had a chain rule situation, we're always multiplying by du dx. But if you multiply by du dx, the du's would cancel, and you would be left with d theta dx. And so this ends up being your derivative rule for the arc sine of any function u. All right, so I can give you anything at this point, and you won't have a problem with it because now you have a model that you can use. And you don't have to go through this entire progression to come up with a solution. So if I said something like d dx of the arc sine of 5x squared, this would be my u. Just follow the model. 1 over the square root of 1 minus my u, which is 5x squared, multiplied by the derivative of the u. That's the only thing that'll make it complicated. If you have trouble finding the derivative of whatever the u is, then you're going to be in for a ride. But otherwise, it's pretty easy. What is the derivative of 5x squared? All right. So the derivative of this arc sine function is that. And it hardly took any effort beyond knowing the rule. All right. Let's do the tangent one now. The cosine, the co-functions, so cosine as it relates to sine, cotangent as it relates to tangent, they're just negations. You can go through the work. I'll give you time to do this on Monday. But when you go through all the work, the arc cosine derivative is just going to be the negative counterpart of this. Not a reciprocal, just a negative. So take that positive one and make it a negative one, and you have the rule for the arc cosine. All right, so practicing this on your own is valuable. It's just you don't actually need to do it to derive the rule.
Like for a test, would we just have to know the rules, or would we have one of those?
You'll have exactly one of these situations where you have to do it on. All right, so again, the result of an inverse trig function is some angle theta. So we can say that theta is equal to the arctan of u, which corresponds to the tangent of theta being equal to u. All right, you can flip it around, or you could just not write the tangent of theta equals u and go directly to u equals tangent of theta. When all is said and done, you're going to need them both anyway, so it doesn't make a difference. But we would then take the derivative of u with respect to theta, du d theta. What's the derivative of tangent of theta? Secant square theta. Start to see why we spend so much time practicing derivative rules. Like when I say derivative of tangent and you immediately come back with secant squared, that was the whole point. So that you're sitting in Calc 1, Calc 2 in college, and the teacher says derivative of secant, and you come back with secant tangent, and the rest of the class is still kind of looking around, being like, where did this black magic come from? Like you'll already have it. All right. So I'm going to do a reciprocal here to get me a d theta du. And I'm going to do a reciprocal here. Now, if you want, do it the opposite of the way I did before, which is to say, okay, well, I know the reciprocal of secant squared is cosine squared. Or you could just write 1 over secant squared. All right, and the rest of it is just cleaning it up. So tangent of theta is u over 1. Opposite side, adjacent side of the corresponding right triangle. The opposite is u. The adjacent is 1. We're just going to need the hypotenuse. One plus u squared under that radical. All right, now the secant function has a ratio of hypotenuse over adjacent, but we're going to be squaring that. So 1 over, I'll take my hypotenuse, put it over the adjacent, and square. And surprisingly, it cleans up because it didn't look like it was going to. D theta du, leave a little space, would be equal to 1 over 1 plus u squared. All right, and that's again because if I square this radical, it's going to go away, leaving me just a 1 plus u squared. Square of 1 is a 1, a fraction over 1 is itself. So this numerator stays as a 1. That whole quantity squared on the bottom just cleans up to a 1 plus u squared, which is really nice. So then all I have to do to get my d theta dx, which is my ultimate goal here, is multiply both sides by du dx. The du's would cancel on the left, leaving you with what you want, d theta dx, and on the right you now have a rule. All right. So we have a rule for sine, we have a rule for tangent, and on Monday we'll have a rule for secant. And then once you have those 3 important trig ratios, the 3 most important trig ratios, then you'll know all their cofunctions. Because all you have to do is slap a negative onto this one, and you have the derivative of the arc cotangent. All right? But again, I mean, it's a journey, so I'll do another one with you on Monday, and then you'll practice the remaining 3 on your own, and then we'll see where we're at. And then we'll mix more of that pre-calc stuff back in. Unit circle, all that good stuff. Yeah. It's a short unit though. I think in the first 5 minutes of class on Monday I will talk you the last thing, the last bit of direct instruction. The rest is practice. We're looking at 14th or so. Okay. 14th, 15th. So again, the result of an inverse trig function is always some angle theta. And so we could draw the conclusion that theta is equal to the arc secant of u. All right. The idea being, again, that we don't know what the derivative of the arc secant is. So if we take the secant of both sides, we'll get something that we can find the derivative of, and that would be secant of theta is equal to u. All right, we're going to write that as u equals the secant of theta, so I could take the derivative. All right, so du d theta, what's the derivative of secant? Secant tan. All right. Again, we want d theta dx eventually, which means we have to do some reciprocal action here. So you could write it as secant theta tangent theta in the denominator, so 1 over all that stuff, or you could actually just use the reciprocals and write it as d theta du is equal to, you know, maybe move the tangent, but keep the secant and take the reciprocal of that. You can go a bunch of different ways with this. But if you were actually just taking reciprocals, it would be the reciprocal of secant, which is cosine, and the reciprocal of tangent, which is cotangent. All right, so that's our derivative in terms of theta. I want to have it in terms of u. All right, so I go back to the original expression, the one that we had before we took the derivative, that secant of theta equals u, make that a u over 1. So the secant ratio is hypotenuse over adjacent. All right, the hypotenuse is u. The adjacent side is 1. What would be my missing side? Square root of what? u squared minus 1. All right, so we have our reference angle theta tucked in there. From that perspective, we have an adjacent, we have an opposite, and we have a hypotenuse. So now it's just a matter of writing, instead of cosine, we would say the adjacent side, which is 1, over the hypotenuse, which is u. And cotangent is the reciprocal of tangent. Tangent has a ratio opposite over adjacent, so I need adjacent over opposite. So 1 over the square root of u squared minus 1 plus twice. So d theta du would be equal to that. But again, what I want is d theta dx. So to make my d theta du into a d theta dx, I'd multiply both sides by what? Du dx. All right, and so the du's would cancel away, leaving us with d theta du. And then this would all combine together to give us 1 over u times the square root of u squared minus 1 times du dx. The only additional component that I'm going to throw on here is I'm going to throw a set of absolute value bars around the u on the outside. And that's because u is taking the place of the hypotenuse in this case. It's actually the only situation out of the 3 that we did where u is part of the hypotenuse. And so it has to be the result of squared values being added together. And so whether those values, the legs of the triangle, are positive or negative in and of themselves, the minute you square them, they become positive. All right? So this must always be positive. Because the hypotenuse is the sum of squared values. And that's also why we don't have plus or minus tacked onto all the radicals that we have for each of the questions that we've done. Right? So anytime we've had a radical, we've always gone with a positive counterpart. Right? Because u itself, if it were a leg, it could be positive or negative, but when it's a hypotenuse, it can only be positive. Right? Because it's a positive measure going out in every possible direction. Question.
So wouldn't it be, for the purple equation, d theta over dx?
Thank you. Thank you. Good. All right, so the remaining questions on this page pretty much work the same way. But what I wanted to do is give you the basically the answers before you get started on those. So let's flip to the top of the next page. I think we did some of them. I don't have them on in this file, so I'm just gonna take it from scratch. So arc sine, and it's really only these values that we've determined. The arc sine of u, we could have had as 1 over the square root of 1 minus u squared times du dx, but the better way to write it would be u prime over the square root of 1 minus u squared. All right, it's more user-friendly that way. All right. The corresponding cosine rule is just going to be the same thing with a negative sign in front of it. So if you wanted to write that in right now, you could. I'll do it in a minute. The tangent, arc tangent, u prime over 1 plus u squared, or u squared plus 1 on the bottom, it doesn't make a difference. The messy one is the secant, which is u prime over the absolute value of u times the square root of u squared minus 1. All right, so all I'm doing is taking my du dx, writing it as u prime instead, just to kind of make it a little simpler, and then multiplying that by the actual fraction, so it goes into the top. Right? It makes it more concise, and it actually saves you some time when it comes to simplifying if that's something you need to do. All right. So then the corresponding rules for our cosine would be negative u prime over the square root of 1 minus u squared. Negative, oh, purple. Negative u prime over 1 plus u squared. And then negative u prime over the absolute value of u times the square root of u squared minus 1. All right. And so what we get at is the idea that, yeah, it's easier to remember these now because all you have to do is remember these and just slap a negative on it. That's not really why I go over this. What this tells us is that if I need to find the derivative or antiderivative involving, when we get to antiderivatives, involving inverse trig functions, the sine and the cosine are only off by a negative number. So generally, you can just get away with knowing the sine information, tangent and secant, and it'll just kind of carry you through the rest of the way. You'll see in more detail what I'm talking about down the line. But for now, as long as you have the idea in your head that the most important trig functions are sine, tangent, and secant, so the functions that don't have cos as part of them, then you're where you should be. All right. So the problems that follow are all asking you to just apply the definitions, the rules that we just came up with. So when it says find the arc sine of 2x, all it's asking us to do is identify the u, take the derivative of that, and then plug it all in. So the 2 would go on top. On the bottom, we'd have 1 minus my u in its original form of 2x as a quantity squared. And if I needed to clean it up, I could pretty easily to 2 over the square root of 1 minus 4x squared. All right, so it's really just plugging and chugging away. Because again, all I'm doing is I'm plugging into this. So identify the u, the thing that's contained within the inverse trig function. Write an equation for that, u equals 2x. Take the derivative, u prime equals 2, and then just plug in. And it works for tangent, secant, cosecant. It gets a little crazier when you get to something like number 4. So let's take a quick look at that one together, and then I'll leave you to it. So it says find the cosine of the arc sine of 3x. There's 2 ways to handle it. One would be to work it as is using the chain rule. The other would be, and so you have a function inside a function inside another function. So that's just beautiful. Or you could write this as an algebraic expression like we did Thursday, and then take the derivative of that algebraic expression. It's pretty user-friendly in its current form because we now know rules for finding the inverse derivative of inverse trig functions. So I'm going to go chain rule. I have the cosine of something. All right, it would have a derivative equal to the negative sine of that same something. Let me go different color there. Cosine has a derivative of negative sine of the arc sine of 3x all right, then I'm going to take the derivative of the arc sine of 3x. All right, so as long as you can pick out your u, you could follow the rules. And it's supposed to be a multiplication symbol. It's not looking too good. I'll just live with it. All right, so following the rule, we know it's u prime over the square root of 1 minus the u itself squared. All right. Now we have a derivative that's solely in terms of x, which is what we were looking for. So that's good. Even though there's signs involved in it, if a question doesn't ask you to simplify, you'd be fine right here. All right, so again, it's chain rule because it's cosine of something, which would be negative sine of that something, but then you have to take the derivative of the something. All right, but quick question, forget about the negative. What is the sine of the arc sine of 3x? It's just a 3x, right? The sine and the arc sine will cancel each other out. So I do have a negative there. So that expression, as ugly as it is, it's just going to simplify down to a negative 3x. And so when you multiply through, you get your final answer in simplest form of negative 9x over the square root of 1 minus 9x squared. All right, so that's by chain rule. It's actually chain rule of the chain rule. But the rules that I gave you above, they all have chain rule embedded in them already. So having arc sine of 3x or x to the 27th power, it doesn't really make any difference in terms of the level of difficulty because it's all following the same rule. Now, the other way of going about doing something like this would be to put it in algebraic form first. So you get a big OR here. Again, it's the cosine, just taking it back to scratch here. Arc sine of 3x. All right, just a reminder, the result of an inverse trig function is always some angle theta. All right, so theta would be equal to the arc sine of 3x. This seems like we're going out of our way to do what we did on the previous page, but we're really not. It's just we're going to set up a triangle here, get in an algebraic form, and then use derivative techniques that you're probably more comfortable with because you've been practicing them for so long. All right, theta is equal to the arc sine of 3x, which means sine of theta would be equal to 3x. We'll write that over 1. All right, so sine of theta is equal to 3x over 1. Opposite side is 3x. Hypotenuse is 1. What's my missing side? Yeah, 1 minus 9x squared. For two reasons. One, because it's Pythagorean theorem. Also, because we just essentially did it. All right. So I'm looking for the cosine of theta. Theta is related to this triangle. Cosine's adjacent over hypotenuse. All right. So algebraically, we're looking at the cosine of theta being equal to the square root of 1 minus 9x squared. All right. But since theta is the arc sine of 3x, it's really telling us that the cosine of the arc sine of 3x is the same as the root of 1 minus 9x squared. All right, that's important because if you don't know the rule for finding the derivative of the arc sine of 3x, the first attempt, the chain rule approach, you're done. There's nothing you can do. You get to that point and you have to stop and throw away like half credit on a problem, right? But here, I don't need to know that because if I wanted the derivative of the cosine of the arc sine of 3x, and I know that cosine of arc sine of 3x is equivalent to the root of 1 minus 9x squared, I could just take the derivative of the radical expression, and whatever that gives me as a result would be the same as the derivative of the cosine of arc sine of 3x. All right, so that would be the same as saying I'll just kind of write this here. 1 minus 9x squared to the 1/2. So chain rule, 1/2 1 minus 9x squared to the negative 1/2 times the derivative on the inside, which would be negative 18x. Which, when you simplify it, gives you the exact same expression. Because 2 goes into negative 18, negative 9 times. This is a radical to the power of 1/2, but because it's negative, it will go to the bottom of the fraction.
Is it okay if we just like do the other way, or like are we gonna have to do both?
You gotta be prepared to go both ways.